All right. So, so thanks for joining me today. So we're talking about something very different than at least I know I do in my day job. And that's talking about software that we can actually play, right? So usually what we're dealing with is stuff that's in some way language-based, something that is based upon words, concepts, numbers, facts, figures, those kinds of things. And what we're talking about today is something I'm very passionate about. It's something that I've actually been doing since I first wrote my first program ages ago, and that's audio and video software. And really what it comes down to is transcending language and not worrying about delivering value. In my day job, I do a lot of agile coaching and technical agility and things like that. So I'm always talking about value. But today we're talking about an experience. And really what it comes down to, the basic thing that you'll see over and over again, is we're going to build something, we're going to play with it, we're going to tinker with it, we're going to play. And then we'll do that over and over again. It's a very different approach. So in this case, too, the development process itself is intended to be about playing. It's intended to be about experimentation. And we're going to do that looking at two different Patcher environments. So the first environment is an open source environment called PureData. The second one is its shinier commercial cousin, and that is Cycling 74's Max. So in the process of talking about these, we're also going to talk about some basics of audio processing and signal processing and synthesis, also video processing. We'll look under the hood a little bit too. It is a developer conference after all, and I know I was curious to figure out how pretty much everything works. When I was a kid, I'd drive my dad and mom crazy because I would take things apart to see how they would work and then just leave them. So they gave me an alarm clock once, and this is an old school one with the little flippy things, right? The plastic flippy things. Dating myself here. And I took it apart, and it was all over the living room floor, but I learned how it worked, and that was great, and that's as far as I cared about. So we want to look at how this works as well. And there's also a couple of things that I have found very interesting. The way that this stuff has to be built, it has to perform incredibly well. And so as a result, that actually has provided some insight into how I would actually code. All right, so from here on out, we're going to dig into PD and Max. We'll talk about how those things work, and we'll tinker a little bit, and we'll play a little bit. So I'll take a moment here just to introduce myself. I'm Krista Campbell. I am an architect, a technical coach, an advocate, a musician, a mom, a trans woman, and a human, obviously. I wrote my first program in BASIC on a Commodore 64 back in like 4th grade. I have, that's awesome. I have a few here that are really appreciating that. It's great. I actually almost brought in my old, I also had a portable SX64, which was about this big, this wide, weighed about 40 pounds. So, but I loved that thing. So, but this is me when I was about 12, and there was a really neat audio synthesis program on there that I spent a lot of time with. And obviously this is me today. So I actually have studied both composition, I've studied electronic music, I've also studied computer science, and in my day job, I'm a software architect at Insight, and do quite a bit in the areas of DevOps and coaching right now. I really enjoy teaching and working with folks. And obviously, I'm also trans. I'm not meaning to be political at all, but it's just who I happen to be, and I'm very fortunate in that I transitioned in 2015. People have been incredibly supportive and wonderful to me. That hasn't been the case for a lot of folks. So regardless of your position and your understanding, I just ask that everybody try to be kind and try to listen to others. And just understand, if you don't understand it, try to at least respect what it happens to be. All right, so let's talk a little more about PD and Max. So both of these, they're very closely related. So PureData and Max, they both were originally written by a guy named Miller Puckett in the 80s in a place called IRCAM in Paris. Anybody heard of IRCAM here? So it's an amazing place. It actually, in France, they actually fund the arts. So there's a famous composer named Pierre Boulez, who founded this place, and it's this mecca of all kinds of just crazy art and interactive sounds, exhibits. They have a room there where it's a 3-story tall building that's built specifically to house a grand piano built into the wall that's 14 feet high. Really neat place. So anyways, a lot of really cool things have come out of Earcom, including the software. So Max was the first thing that was built, and it was actually initially just MIDI. And for those of you that appreciate my Commodore 64 stuff, you'll probably appreciate MIDI as well, or any musicians here. So it's the old standard for communicating between typically musical devices. So, and they eventually expanded that to include audio processing, real-time audio processing, which is what we're focusing on here. So that was actually bought by a fellow developer, David Zaccarelli, who commercialized it, started a company called Cycling 74, and that's really where Max came out. Excuse me. And PureData, on the other hand, has always been open source. And so the idea behind PureData and why it's called PureData, the idea was that they wanted to be able, MillerPuckett wanted to create an environment that would basically allow for interactivity with any kind of arbitrary data structures, right? So the original idea was from the compositional side of things. People were wanting to be able to create a visual score, effectively an image, that could then be played somehow. And that was kind of all the rage back then, interactive scores and compositions and stuff like that. That was kind of the idea. And the other flip side of that is interactivity, right? So being able to interface with this in a various number of ways. And that's with what we call control data. And control data is basically what hooks up any kind of interface we have, for example, a mouse, keyboard, whatever, to our system, and making that relatively transparent. Later, they added real-time signal processing. They later also added video processing, but it's primarily used for audio processing still. As I mentioned about video processing, there are real-time video processing libraries in both of these environments. PD has one called GEM. Maxcall has one called Jitter. And we'll actually look at that a little bit here, too. The main audio engine for both, they still share some of the same source code. And it is the uber geeky part of myself. I am fascinated by it because it's so elegant. So we'll look at some of the implementation of that actually in a little bit. So let's talk about PureData a little bit more here. So as I mentioned, it's open source, it's free, it's vast. It's this massive environment that just keeps growing and growing and growing. People are always contributing to it. There's still an active development committee. I think it was in March was the most recent build, so it's been pretty recent, and they're keeping it up, which is good for an open source project that effectively started almost 40 years ago. It's very well documented, and it's also a great way to learn about audio, synthesis, signal processing. So MillerPuckett actually wrote this book, and it uses examples built into PD itself, steps you right through all the different aspects of some of those fundamentals, and you can really do some cool stuff after that. So it's also written in C and C++, and it's incredibly portable. So Max is also vast, and it's very polished. It is obviously a commercial product. It's actually the basis for a lot of software. Have you guys, anybody here heard of Ableton Live? Yeah. So Ableton Live was actually a project that started with developers at Cycling 74. It was originally prototyped in this environment. And eventually, after Ableton took off, Ableton eventually bought Cycling 74, and they incorporated a thing called Max for Live, which is basically a Max hosted inside Ableton. So, and actually all the things that we built with that also are available in Max as well. So it's a really neat kind of community of developers there. So it's used to create a number of different things. typically, we've seen it used to create things like plugins. So those are like virtual effects pedals and things like that in the VST or AU format, virtual synth samplers. But there's so many different other uses, and it's expanded to do very recently, some code generation capabilities, which is really incredible as well. As I mentioned, much prettier. And it's actually typically used by developers as well as musicians, whereas PD is more on the development side, usually more on the experimental side. So I mentioned about the code generation capabilities. So there's a component called Gen, which is kind of the basis for the new hotness within Max. There's a product called RNBO, which uses Gen, and that can actually generate actual code, C and C++ code, that can actually be ported pretty much anywhere. And it runs on Windows and Mac, and it's actually very affordable now. So when I first started getting into it as a college student, it was like $700 for a license, and now you can get it for $10 a month. OK, so that's PD and Max. So what is a patcher? So a patcher is basically, it's a type of a data flow language, which is a very different way of looking at development, right? So I think probably most of you are familiar with procedural languages, where we have a list of instructions, and then we have object-oriented languages, where we're interacting with objects. So in a data flow language, it's kind of like a massive Rube Goldberg machine. So think like beginning of Back to the Future with Doc Brown's, alarm clock coffee maker that feeds the dog that isn't there, obviously. Those kinds of things. You have some event that happens at the top, and that then trickles down and causes a whole series of events to happen. And so in this case, it's defined visually. We have basically a series of objects that are represented by boxes, and then those are connected by lines that represent messages and also signals. The boxes themselves can be thought of as objects. They both have variables, state, as well as code to actually execute things. And again, the lines represent variable assignment, different calls to functions, and/or audio signals. And so there's a number of different ways to trigger the downstream objects. That could be a control signal. It could be pressing a key on a keyboard. It could be a thing called a bang, which is literally an object that is basically you're hitting it to start it. And then we have timers, things like that. OK, so once again, what is the patcher? So this is one of the earliest synthesizers by Bob Moog. And basically, back in that day, we had these different physical things that actually were then chained together with physical cables, right? So not unlike an old telephone switching room, we had people that are connecting things up, right? So the model for both of these systems is basically a virtualization of this. So each of the different boxes there does a different purpose. You have things that are generative, things that create sound waves, maybe simple sine waves, sawtooth waves, whatever. You run that maybe into a thing that might create some kind of maybe vibrato, like an oscillator that changes the pitch slightly. And so if you hook that up to the amplitude of something else, then that can actually create a whole different type of sound. So you build these things together, and that's kind of the initial module and concept around patchers. And the windows that we work in, they're all called patchers. So that's the basic ideas. So let's tinker a little bit. And in this case, once again, I apologize. We're having slight audio issues here, so we'll see if we can make do. But we'll definitely get into the environment. So we're going to start off. We're going to do all these in PD just because PD itself tends to be a lot easier to work with initially. It's a little bit less overwhelming. And we're focusing initially on the audio engine piece of this. And so basically what we're doing here is we're going to test the audio, which is the audio engine, the DSP engine. You'll see DSP all over and all this stuff. It stands for digital signal processing. It's the thing that really does all sound processing and generation. It has to run extremely efficiently. It has to basically calculate, at a minimum, 44,100 samples every second. And if you consider that's for every single box that processes audio in the patcher. So they're usually, well, at least at this point with the performance of most modern computers, it's not as bad, but there's a lot of CPU overhead in DSP. So let me go back over here to this. We'll see if we can hear this through the microphone. I'm going to have to pop out here and pop over to my Windows side. So in here, we have, so within, this is a basic, I'll actually start this over for you guys. So this is actually a patch that I wrote last time. We're going to play with this in just a little bit. But within any PD window in media, we have a tester, test audio and MIDI. And that's what this is. And again, PD is not meant to look beautiful and shiny, but it does some pretty amazing things. And within here, we can basically test the audio generation capabilities by running test tones here. We can also test things if we had like any kind of like a keyboard, like an actual musical keyboard, hooked up via MIDI. We can also test audio input and output. So I'm just going to create a simple test tone here. And it's coming through on my machine. I don't know if you guys are able to hear that at all. You can? Good. Excellent. Cool. OK, so we got some audio in there. That's good. Great. So, all right, so that's the first piece. And an important point here, back to that whole DSP idea. So this switch up here, DSP on or off. So if I turn off the engine, any sound that I have playing is going to stop. So once again here, if I have a test tone and I turn the DSP off, then the entire DSP network behind this is stopped. So obviously there's no more sound. All right, so back here. That's just the basics to make sure it's running. And next thing we're going to talk about is just some of the basic objects and how they interact. So there's only really a handful of different types of objects in both of these different environments, and then literally thousands of variations upon them. So, and these are the three most essential ones. So we have a message box. In PD, it has kind of like a little edge, almost like a flag on its side. And so then we have that connected up to an object box. In this case, the object box is a simple addition object. And then we have a number box at the end, which actually is it's a user interface component that's visualizing its value. And we see across the left here, we have these connected together. And in this case, each one of those connections represents data flowing. So when we click on that message box, it's going to send that number to the object box. And the object box is going to take that number in this case, and it's going to add whatever number happens to be there, 13 in this case. Then we see its output. So these inlets and outlets that you see here, they are basically the ones on the far left are called active. So when something happens there, that actually behind the scenes is basically doing a method or a function call. It's doing some action. So everything to the right of that is basically setting some kind of variable. So for object-oriented folks, it's like basically setting your properties. So you can think of those as like basically setters. So they're passive in that they'll set values. They don't actually do something unless something happens on the far left. So let's go ahead and just build. Actually, because we have a little bit of interest, well, I'll get to the next one, then we'll go ahead and build this one here. So, so moving forward from that, those were simple objects, and then this is an audio object. So, and this is literally the simplest possible synthesizer you can build. And you'll see here the audio objects have like a little tilde at the end, and that's indicating that it's an audio rate object. So what happens in those, we have two types of data flowing now. So the really thin lines that we see, that's called message data. And that basically happens kind of like a standard function call, right? So and it only happens when a message changes or it's explicitly sent. So the thicker lines that we see here, and in Max it's represented, everything in Max is prettier, but basically it's kind of like the like little yellow lines across it to really show that what it is. That actually is the audio signal. And so that is a lot more data that's flowing through. So the basic approach of the most simple kind of synthesizer we have here is that we're basically just creating the simplest possible wave, which is a sine wave. That's what this OSC object does. And then we're basically going to, actually something we always have to do, we need to scale that. So we want to make sure it's not going to blast at full volume, which is by default what it does. and then we're going to actually output that. So let's go ahead and build this. Let's see if I can get over here. There we go. Apologies. Okay, there we go. And back here. Yay. All right, let's build a very, very simple synthesizer. So I'm just going to create a new patch here. And within here, we're going to start with that oscillator. Apologize if the font is a little bit small here. So I'm going to type in, I just said put in object, OSC and a tilde. And that built an oscillator. And then within here, we're going to put a message. And that's going to be its frequency. Actually, let's create a box for a number here. We can change it this way. This is going to set its frequency. It's also going to change it because I'm hooking it up to the leftmost inlet. Again, that's the active inlet. Then we're going to take that, as I mentioned, we need to make sure we scale that thing. So we're going to put a multiplier here. And it's the standard multiplier, asterisk, with a tilde. And so that's not just multiplying against a single individual value. All of these signal types of data, they're actually not individual values, they're buffers. So if you are doing any kind of audio stuff and you hear things talking about, the buffer size, it's because almost all audio is processed in chunks and arrays for performance optimization. And so in this case, it's not multiplying against a single value, it's going to scale every single number in that array. That array basically represents a very small chunk of sound, very short duration of sound. So, and we're going to add a couple of messages on here to set the value of that thing. Let's say 0, so we can turn it off. And I'll put that over here, and then we're going to put a message here as well. And we're just going to say 0.2 to stay safe. Finally, we're going to output it. We do that with an object called a DAC. We'll talk about that in a second, what that means. But that basically is what takes our digital signal, translates it into something we can hear. So now that we have all this, I'm going to basically, there's an edit mode, and then I'm going to lock that so we can actually play with it. And then I'll make sure that my DSP is on, which it is. Excellent. So, and let's see here. We have some sound. There we go. So I'm just adjusting the frequency here by clicking on this, moving my mouse around, and it's changing that in real time, of course. If I click on the 0, it's going to set that multiplier to 0, so no sound's coming through. And then that's essentially it. So the simplest possible synthesizer you can build. So within PD, they have a relatively limited set of PB objects, and these really haven't changed for a very long period of time. There's a lot more once again in Max, but basically the idea of these is to give you something that you can work with that can visualize this, and then again, folks typically, when they're working with this, it's more for their own projects, academic projects, things like that, or embedding it. If you actually want to build something that somebody's going to interact with, usually you're going to be doing that within Max. And one of the problems with these patch cables is that they can start looking very, very crazy and unruly very easily. It reminds me a little bit of the meme from It's Always Sunny in Philadelphia, right? So that guy, you don't want your patches to look like that. So we basically are able to simplify our patches by using things called send and receive ports. And it's just like it sounds like. Basically, you have a send port, has some ID on it. You have a receive port with the same ID. Value is going to be moved from one to the other. This also is showing something else I wanted to point out, which is one of the things I love about these environments. The help files themselves are available for everything. And those help files also are themselves patches. They're playable. You can copy it and build something else out of it. It's a great way to learn and mess around, right? So anytime you're in any of these environments, you can always right-click on it, do help, and you can see the thing and play it. So let's look into the hood just a little bit and talk about how this is actually implemented. Some of this stuff is probably going to be a review for you guys, but I want to make sure that we cover it. So let's just talk a little bit about how digital audio works, right? So So basically, sound, as we all know, it's the movement of air molecules, right? So that hits our eardrum. What those vibrations do, that moves our eardrum and some of those thousands of little hairs in our ear, and our brain then interprets that as sound. So how does a speaker work? Well, a speaker basically has a surface that we're moving very rapidly, and that surface actually then moves the air, and that actually will then in turn reach our eardrum and reach our little cilia in there, and we end up hearing the sound. So in digital audio, what do? Well, basically we have sound waves, which we're all familiar with seeing, right? So I'm sure we've all seen, if we're sending an audio message anywhere, usually it's visualized as a waveform like this. What does that actually mean? Well, the distance of this wave from the center, that is basically the loudness. That's basically how far are we moving the speaker head by a magnet, right? And then how close those things are together are the frequency of what that is that we're hearing. And so basically you can think of this as the position of the speaker head relative to its center position. So when we're looking at an environment like PD and Max, and really any digital environment, when we're dealing with the environment itself, we're dealing with samples, right? And the samples are typical integers or typically whole numbers. And so we have to have some way to convert those numbers into an analog number or vice versa. So when sound comes in, it's a voltage that's analog. We want to convert that into a digital number. That's an analog to digital converter, surprisingly. And then going out is the opposite. We basically have digital values we want to convert into analog signals, and that's done by the DAC. So audio input is always the ADC tilde. Output's always the DAC tilde. Those also, we can actually send a message to those. And one of our simple messages is an X, as you see in both examples here. That's a checkbox, basically. And by sending that message into either of these, it's going to turn off all the audio processing as well. So it does turn off that ESP. So talking about the actual objects and how they're built. So PD and Max, the non-simple objects, the simpler objects, they're all implemented in C and C++, as most of the stuff is. And again, think about how old this is. Performance and the amount of computational requirements for this back in the 80s made real-time signal processing impossible unless you're like using a supercomputer or actual dedicated hardware, until we got in the 90s, and then it became possible usually on Macs and some specialized devices. And then now we can pretty much do it anywhere. But that's all implemented in C and C++. The source code that we see here is a little weird. I haven't used C since like the 90s, and I've used C++ quite a bit over the years. But usually when we see these examples, we're going to see something it's basically a C representation in C++, which basically is they actually C++ transpiles to C, if you guys weren't aware of that. Basically, it's just every method has a pointer to the actual object itself. We'll see that in just a second. Basically, there's a couple of different methods here. There's one that is called, that basically sets up the constructor. Basically says, how do we build this object? And so you register the constructor with the engine. And then you also register a number of different message handlers. So for example, in the synth that we just built, we had messages that were numbers, right? So the object, when we first created it, it registered that, hey, I can handle messages that happen to be numbers, that kind of thing. So when the object then is finally actually instantiated, new is called. It actually builds its outlets and inlets. And then the engine calls the appropriate message handler whenever data is sent to the object. So we have this is really interacting with the messaging system or the messaging engine inside Max or PD. And so here is a very, very simple object. It's a counter. As I mentioned, a little bit ugly to read here, but basically what's happening, I wanted to point out to you guys, is that the way this is also coded, of course, is that we have to declare things before we use them. So we kind of read this backwards, right? So the first thing we have here is a setup function, which basically is, again, it's saying, hey, this is how you actually create me. It's class new. It's registering its constructor. And it also registers the types of messages it can handle. In this case, we have add bangs. We can handle a bang type of message. And then we have the actual implementation of that new, which is its constructor. It creates its outlets and inlets. And then we have implementations of those different message handlers. That's basically the structure of it. So when, in this case, a bang message, which is just, again, it's just like a little circle that we touch, it's going to call this method. So now we look at audio objects, signal objects, again, the tilde objects, right? So basically, to support this, what PD and Max do, they basically extend this to do, and this is incredibly elegant. This is where I really geek out over different types of code, but it basically just adds two different functions. What those functions are, basically, there's one called the name of the class underscore DSP. What that basically does is it registers the perform method into the DSP tree. And so what is the DSP tree? This is really how the entire thing works. So basically, the DSP tree is all the signals starting from wherever we have a signal originating. That could be like an oscillator, like we saw in our super simple synthesizer. It could be an analog to digital converter, which could be a microphone input. Whatever that is, it basically models that from the top all the way down through the patch. And so it creates basically a tree of each signal processing object. And so what has to happen is that when the DSP is on, it's going to be calling each one of those objects in order very, very, very quickly over and over and over again to process the audio that happens to be there. And so it's visualized as these different lines that are connecting these things. But the way that we actually handle it is that each one of those lines is actually the exact same set of data. It's the exact same array. There's a pointer to that same array that's patched to each one of the objects. And each one of those objects then does whatever it needs to do on it when its perform operation is called. And that's the second of the two functions I mentioned. So DSP says, hey, when you are going to, actually when you turn the DSP engine on, it calls the DSP method, and that says, hey, I'm going to register my perform method. And that basically is the one that's called over and over and over again very fast to process those signals. So because we're processing these as they're basically pointers to arrays, right? So in memory, it's literally the same array that's being passed to each one of those objects. And each object is then just working on whatever it needs to do on that array. And so in the DSP tree, the job of the engine is to call those methods in the right order and to call them very, very, very quickly. So by doing this, this is what allows this to be incredibly optimized, right? So we're not reinitializing memory. We're not adding new things in. For each one of those different objects, when DSP is on, it literally is it's actually as if all these different objects are looking at the same thing. And the first one's saying, hey, it's your turn. Great. I'm going to do my first thing. I'm going to make the waveform. OK. And then at the very end, in this case, we have the multiplier. OK, my job is to scale that. I'm going to take all the different samples in there and make them multiply by whatever my scalar is. So that's the way that it basically fits together. So and this is basically how the optimization of these types of data flow patchers are built. And so this is an example of a crossfader object. And there's a lot here, but all I wanted to point out to you guys, really, once again, we have to start from the end and go to the beginning, but in its setup method here. And this is, I'm so glad we don't code in C anymore, but professionally at least, but basically it's registering in here the DSP, and that's that actual method that is set up when we turn that DSP on, adding its perform method into that network. And that happens back here in, here it is, yeah, DSP. And so what this is going to do is add to the network. It's going to add its perform method. And what you see in here, it's handling, what's passed to it is a pointer to a signal vector, which basically means it's an array of arrays. It's basically a table of these signal vectors. They're all the same size. And so each one of those represents audio passed to a different inlet and audio that's then passed to a different outlet. And so finally, when the thing's actually running, it's going to be calling its perform method over and over and over again every so many milliseconds, depending on how fast your sample rate is and how big your buffer is, in order to make sure that we're processing all the samples we need to be able to generate our sound. That's basically how all that stuff fits together. So that's all the theory. And so now we can get into doing a little bit more playing. I can show you some of the really cool things that we could do with these different types of environments. So one of the things about this that's so cool and that I think is, it's kind of a, whenever I even interact with it myself, it's usually I'm going to kiss several hours goodbye because there's just so many different fun things to mess around with. I always find something new. But PD and Max are both initially built to be interfaces, right, between humans and various software, right? So that was from the beginning of the initial design. They wanted to make sure that that was always a possibility and always supported. And it started off with very simple interfaces based upon MIDI, but over time they've added so many different kind of things. And there's pretty much any kind of controller out there you can think of. There is an interface in both these environments for that controller. So here are a few examples that we see. There's actually a Wii switch that we have here. There's a specialized touchscreen thing called Mira. There are iPad, iOS, Android, so many different interfaces for all these things. There are specialized devices here that you see too. But basically, you can make any single thing interface with the interfaces. So one of the ones I'll show you first, which I think is really interesting, and I actually just realized this one very recently, is leveraging the control data of an actual phone. And so we'll look at that first. This is actually a thing called, it's an app you can download. If you have an iOS phone, you can download, it's called PD Party. In the Android world, it's called PD Droid Party. And basically, this is built by an academic who also liked to do really interesting performance art. And he basically would dress up as this like living television almost. It's like a television helmet. And I should have included a picture here, apologies. But, and he has wearable tech, basically is synthesizing and processing things as he's doing movements. So those are the kinds of projects a lot of times that people make with some of this stuff. So let's see if we can get this going here, and we can show you guys a few fun things. All right. Now, hopefully we're able to hear our audio here as well. All right. Okay, I'm going to hop out of the presentation real quick here. So I don't know if you guys know this or not. For those of you that have Macs, you can actually plug your phone in and run QuickTime, do a movie recording, and then that becomes your video source. And I think we see that now. Yeah, we do. Excellent. All right. Make sure the audio is coming through as well. Good. OK. Great. So yeah, so this is basically a port of PD that's actually running on my iPhone. And basically, all these ports kind of have the same approach. We haven't gotten into the ins and outs of this, but when you get into like building more complex patches and stuff like that, you kind of, it's almost like an MVC, a model view controller kind of approach. You usually have a presentation layer or view. Behind that, you have all of your patchers and all the complicated connections and all the guts, basically. So what you see here and what you interact with are basically just presentation layers, and those then are behind the scenes running these patches. This actually is, these patches here are from another application that I think they stopped maintaining it about a couple years ago, called RJDJ, which is another PD port to iOS. I'm going to be careful here to make sure I'm not going to hurt anybody's ears. So we're going to turn this down first. And I'm going to play with. Can of beets. Here. For 1 second here, we just had this working a second ago. Try that instead. You should be able to see this here. Okay. Again, of course, we always have technical problems the one time that I'm projecting and sharing this with you. Bear with me for 1 moment. I'm going to actually disconnect this first, and then we'll reconnect that. It's also always the risk of doing any kind of demonstration with technology like this is you never know what you're going to, something is always going to happen when you actually go to do it, no matter how times you practice it. Okay, MSC disabled. Settings. Good. Good. There we go. Excellent. There we go. Let's make sure we have audio. Which I don't think you guys are hearing at this point. Oh, I see. There we are. So what this patch is doing is, it's really fascinating. So it's actually using the accelerometer on my phone, and also its gyroscope and all those, obviously all the different sensors here, that's all control data that's being used, in this case, to move these little balls around in this grid. And then whenever the ball goes into one of the squares, it's then synthesizing some kind of sound or playing a sample in each one of those. So it's kind of a neat example of the different ways we can control this, control these patches with novel control data, which in this case is our phone. That's a fun one. Another one here that I thought was really funny was can of beets. It's going to respond to me here. Yeah, so basically here, I'll do this so you guys can see my mouse. Hopefully. No, it's not looking there, of course. And basically, we have our little can of beets here, which I also like because my last name is Campbell, so I've had Campbell's soup jokes my entire life. But as I move my finger across here, it's in real time, it's changing this step sequencer. And then if I shake it, it changes what it's doing. And then the last one I want to show you from here is one called Eargasm by a guy named Damien Stewart. It's actually from RJDJ. And this one, hopefully this will work for us. It actually takes real-time audio, and this time it's recording my voice, and then it's processing it and kind of expanding it. It's adding different types of reverb to it, and then extending it. And usually best played with headphones on so you don't have feedback like that, but it's a really, really fun one to play with. Cool. All right, so that is RJDJ. All right. All right, so next I'm going to show you guys what I actually presented last time, which is my audio microscope. And as you can see here, I don't have mad UX skills at all. It looks really bad, but it actually does some really cool stuff. Basically, what this thing does is the goal of the exercise when I was working on this was to try to figure out how I can zoom into a sound that's playing. And I wanted to be able to basically pause and look at a spot, a chunk of that audio. And the problem is whenever you stop in conventional audio players, right, there's nothing to move your speaker, so the sound completely stops. So solving that problem actually is a really, really challenging one. And in the presentation, I went through like it deals with psychoacoustics, because we basically have to fool our ears into thinking that we're hearing that same chunk of sound over and over again. So, and that was quite a rabbit hole to figure out. We have to do all kinds of like complex math and Fourier transform. We use Euler's law, all those different things. But basically what it does is it takes the sound, right, and it does a Fourier transform on it, which basically takes it and flips it into a bunch of little bits of each frequency band. So those of you that are familiar with like graphic equalizers from back in the day, so think about that as a 1024 band graphic equalizer, you know, a little itty bitty piece of sound, a little sine wave for each one of all the different things that make up a sound. And it's doing that really fast. It analyzes that, and then it has a bunch of oscillators basically that are recreating that, each one of those little bands over and over again. So it's basically resynthesizing that little chunk of sound over and over again. And the result of that is that you basically can stretch something infinitely long. You can basically stretch it and stay in one part of a sound forever. Sorry. And so in here, I'll show you how we put this together. Basically, organize this in a few different sections, but we basically have a sample that we're going to load in here. We're not going to do any kind of recording in this example. And I basically show we have two different types of playback. We have the basic conventional playback, and then we have the phase vocoder, which is what we actually use to be able to zoom into the sound. So we'll pop over there for that one. All right, so let's pull the. So right here, I actually, there we go. And I'm going to load our sample in here. Again, as far as kind of this thing's put together, what we have down here, I actually have a bang, one of those little circles that basically fires off one of these networks, and it's sending a message called open panel to another message that says read sample. Basically, that behind the scenes is adding that into a buffer. And samples here are just stored as raw arrays. It's just a raw bit of data, that's it. And so we're just going to pull that right into there. And that's typically how you build some of the more standard things that you would do in a conventional application. You still have to do it within this kind of world. One of the asides there is that doing something simple like loading a sample and opening up a simple file dialog, right? That's kind of painful to do this way. You can do it this way. But they've extended all these environments to support different scripting languages. So JavaScript, Node.js is something they just added to Max as well. So, and a number of different languages as well to make it simple. So let's pull in some of the audio here. Actually, I have some songs from Guardians of the Galaxy. All right, so I've loaded in my sample. And so you can see that's in this array here. And this, again, this is just a bunch of numbers visualized as a graph for us. And so I'm going to actually play this in its conventional way. I bet most of you can recognize this. So in this example, we are basically, this part of the patch, all it's doing is just reading through this array, and there's another one of our objects that basically is just a sample player, and all it's doing is just reading each one of those samples, and it interpolates between them, and it's able to actually play back. And so very simple, but also if I change the speed that I'm reading through that, it's going to start slowing down and also deepening the, the pitch until we get to 0. And at 0, it's going to stop. Let's see, there we go. So it totally stops. So, and that's of course because there's nothing, there's no more movement that's happening here. So with our vocoder, basically we don't have that problem. So I'm going to start this one here. I'm going to turn it down so it doesn't hurt you guys' ears. You hear this a lot of times. It sounds a little bit like there's some overtones and a little bit of droning. And that's actually caused by this effect called windowing. So whenever you take something and you break it up into little itty-bitty pieces, there's some artifacts to the sound, and that's just a thing you have to deal with in signal processing. We're going to start proceeding through this. This is at 50%. I'm going to pause it right when this stops. So right now, we're at that one spot. I'm going to proceed through it very, very, very slowly. But what it's doing, I can stop at any of these places right there, and it can just sit here forever. It's taking that little chunk of music, and it's basically resynthesizing that over and over again. And that's when we have the illusion that it's actually playing even though we're not playing. That's how that fits together. So you can do all kinds of really fun things with that too. You can also do things like change the pitch independent of the actual speed, right? So if I wanted to make this like a Chipmunks version, so I think the folks that did the Chipmunks back in the day would have loved something like that because they had to record everything half speed and speed it up, so here it just does it. So, this is one of those things that I'm so fascinated about. If you're ever curious about like how something like this works, I'm always happy to talk about it. But it's a great big huge rabbit hole of how all these different things fit together. One of the things I didn't mention to you is also as far as like structuring these patches and how they work. You can, aside from having the idea of a presentation layer, and having your actual implementation behind that. You can do things like reusability and modularity. You can do that by basically having subpatchers. And this is a subpatcher that's kind of a mess. It's kind of like the Always Sunny in Philadelphia version. So, but that's that patch that I built. And the last thing I'll actually show you guys is video. I'm here for that. So within Max here, this is relatively just recently released. It's called, I think, on Visi. And so what Visi allows us to do is take real-time video input. And in this case, here we are. Of course, right now it's going to play for us. And we should be able to see the output of this. Nope. Okay, once again, I think it's an issue related to it going over HDMI. One moment here. Yeah. Yeah, let's just do one here from scratch. Basically, the idea of Visi, and this is a blank Max patcher, so we can basically start with any kind of input, right? So this is our video input here. And it looks like for some reason here it's not allowing us to pull it in. But this should allow us to pull in from the camera that I have here or from my FaceTime. And then we can actually take that and we can transform that in real time and render all kinds of neat and fun things. So once again, there's always the risks of doing any kind of device-based stuff in a presentation. But it's really neat. You can apply all kinds of different patterns and fractals and things like that in real time to your video. And you can also, it gets really fun when you can basically change video processing based upon audio processing. And that's actually what I did in the patch that I was going to show you guys. Obviously, it's not functioning right now. But basically, it takes in the video signal here, and then it actually takes in audio, and it'll do things like rotate it, emboss it. It actually granulates it and stuff like that in real time, so it's very neat. So I know we're about out of time here, and that's basically all I wanted to share with you all. So the thing about this stuff that's really fun is that in the process of doing this, typically, you're playing while you're building things. And that is just a whole different way of interacting and working with software that I think is just a really fun way to spend your time. So thank you all for your time.